Yeah, I have it now. I think we can even start. So let me try to check. Uh, do I even have the correct one here? Or maybe the semester one? Oh no, I have the semester one, not the second semester. Can you please, guys, please share um the second semester learner guide for physics so that we can start. I'm still waiting um for the learner guide so that we can start. And the time is running now. So today I don't have the learner guide yet, but I'm still waiting for someone to send it to me. So I think we can even start so far while I'm still waiting for the learner guide. So so far today you said you guys you are writing on Saturday. So I think today it will be fine so that we can start with the simple harmonic motion, also the elasticity for the string. So so far sorry,
Number, third means is 4.5.
can you all hear me?
Yeah, right? I know.
Mr. Zulu, can you please switch off your camera? Thank you. Can someone please send me the learner guide on WhatsApp for semester two? Thank you. Tango, I got it. Let me download it. I hope you can hear me now. Studying unit three. So before we can start, do you all understand unit two, the rotational? Do
Yes,
you all guys? Oh, you understand unit two?
yes, we do, sir.
Okay. That's great. So that's fine. I think this will be more easy. So I'm just that they see they need assistance with unit three, and I don't know why. Maybe you can tell me better. Okay, it's fine. I have it here. Let's hope you can see. So here, um, I wanna it's fine. So okay, this yes, you're in the three. So if you can check here, we'll be dealing with the spring. Sorry, with the spring, and then if you can check, we have the motion, have the elasticity, and but here we'll be dealing with the one harmonic. So if you can check, this not the first thing you know about the angular units. So as you know that lastly we're dealing with the rad per second for angular velocity, and then as you know that for the acceleration you were dealing with the rad per second square. Just all about the the rad only, but for these actually represent the motion likely to be in revolutions, where we deal with the 2 pi. As you know that the 2 pi is one revolution. Some would likely to say one rev. Sometimes they can say rev per minute, some other way. So here we can check, we have angular frequency, and then as defined as the number of circular revolution given in a time. So as you know that has still this SI unit, which is per second in that way. So here we'll be focusing on the frequency, we're focusing on the period. As you know that the period is the time taken to complete the one revolution. So before we can start, so as you know that here we've been given the angular velocity. Let me just this angular velocity. Let me just use the velocity only. This is the angular velocity, which is have the relationship with the frequency. So here, as you know that the frequency it has an or per second. So this comes from the time where we deal with the period, which is one. Period is equals to 1 divided by the frequency. So the frequency is that one that we're gonna got here. As you know that we can even got the frequency such a 2 pi. Um, and then oh sorry, I'm making some mistakes. To be other way. And then frequency should be in this way. So we can even calculate the frequency. We can also even calculate the frequency. So even frequency can be, sorry. So as you know that for this, okay, let me try to use this blank sheet. I think this will be more better. So as you know that I've been given the angular velocity, which is 2 pi, the frequency. So for us to find the frequency, so we need to say that the angular velocity divided by the 2 pi. And also this frequency can also be written as 1 divided by the period. Remember, this period is the is the time required to complete the one revolution. As you know that the revolution is 2 pi. So this is one revolution, as you know. So if you can forget about that, I don't know. So you need to know that one revolution, it's all about 2 pi. So from there, when we go back to our learner guide, so here we'll be focusing on the first term. So reason is restoring force. Okay, restoring force of a spring. So actually, this force actually apply when it bring the system back to the equilibrium. Bring back the system back to the equilibrium. So remember, if you stretch the string, if you can check here, we have the string which is unstretched. But when you oh sorry, when you stretch that string, um, it's going to extend and then comes to this point. But remember, as you know that when you extend this string into this way in this position, remember you apply a force, and also there is another force that is keeping you to the other side. As you know that here we might even be dealing with the weight, which is mg, and then we be also dealing with the f. As you know that f is equals to ma. So this f here is still the same as ma. So you might even require to calculate the acceleration of a mass and get the acceleration there. So in an easier way, can be even written ma equals to negative k, which is a spring constant, and then also the displacement. So the displacement is the displacement of the spring from the original or the equilibrium. Remember, we talked about the restoring force. Remember, as I said that this this force is required to bring back the system to equilibrium. So okay, so I think we can from this point we also be focusing on this graph here. So this graphic, if you can check here, we have the amplitude. As you know that the amplitude is from remember from the starting up to the let me say the to the maximum height of the graph. So this is the maximum height. As you know that the velocity will be zero. As you guys know about it. So from this point and that from this point to this point, as you know that it's gonna be something there. So you guys need to know that there is a change. So if there is a change in x, so we might even have velocity. As you know that v can be also written as root of 2 times gravitational acceleration times height. It's all about that. So that h it can be also be um, this changing x for you to get the velocity. Okay, Jauge can ask.
How did you arrive to that formula? That V is equal to square root of 2gh.
Okay, so okay, it's fine. Let me try to share the other side. So you are asking that how did I manage to get to that formula? So actually, that formula you guys need to know it by your heart, because if you don't know it, you're gonna get lost most of the time. So remember, let's take we have okay, we have the ball here, and then this is our ground. Okay, let me try to fix this. Okay. Okay, let's say we have a ball here. So we have a ball here. Let's say this being from a certain building, certain height. It's fine. Say this is 50 meter. So as you know that if this ball is being dropped, so the velocity or the v initial is going to be zero. Remember, it's being dropped. It's not being projected or being thrown. It's just being dropped. As you know that this you have v f squared is equals to v I squared. Or let me just focus. Okay, fine. Gonna fix it. So the v final squared equals to the v initial squared plus 2 times the gravitational acceleration times the change in y. So remember, I managed to write the change in y since we are dealing with the height, with the vertical height. So if the initial velocity at zero, so as you know that anything time to the power zero, it's gonna be that zero. So we're going to left with the f squared, vf squared, uh, to a change in y. So this still are the same as v f equals to root of 2 a, and then change in y. Think there is another hand. Oh, but maybe we have another hand. It's fine. So as I was saying that from that point, so as we have changing one, so that this changing one we can even change it. So this is gonna be our height. See, this is our height. So just gonna write 2 times the a. So this is acceleration. Can even write the gravitational acceleration. as you know that we are dealing with the vertical. So also there we can also write h. So this formula is from here. So this formula can assist you in many things, especially even to this part where you need the velocity from that point. Mr. Jago, do you understand, sir?
Yes.
Okay, let's hope you're with me. So as I was saying that you need to know this formula by your heart. If you don't know it, just start uh, to memorize it or also to put inside your heart so that it can go everywhere with it. So it's fine. So from this point, we'll be having the amplitude, also be having the period. As you know that the period, if you can check here from this point up until we go to the other side, this is the half period, and then from this point to the other to this point. So now you have the full period. So the period it's worked in this way. It's not like this displacement, but from this point up until 2 goes down and then come to that point. It's the way we call the period. So you guys also need to know the relationship between them. Okay, it's fine. The displacement of the string, also the force. So remember this negative k. Before I can go, are you guys with the physics practicals? Have you all started with the physics practicals?
Yeah, yes, sir. We have started.
So yeah, I think maybe I don't know how you guys managed to start the physics practicals without the knowledge of this one. Because I think this one is the first practical that you should do, but it's fine. So as I was saying that we have this k here on this point. So that k we get that k from F divided by X. So as you know that force it's okay, let me try to use this side. So as you know that force, okay, write the formula Kx is Kx, this is the constant for the spring. And then for us to find this K, we're gonna say K is equals to negative force divided by X. Okay, so in this point, as you know that force it's as Newton and then X will be meter. So our K will be measured in Newton per meter. So now you already know that your constant should be in this form. Should be in Newton per meter to get the constant. So from that point, you also need to know when we talk about the Newton, we talk about what? So before I can go further with this, I want you to pass through somewhere. So as you know, this from things from I don't know from grade 11, the F net is equals to MA. So where you have now you have the F net. So you have been told that the F net is equals to MA. So you know that this is Newton equals to, remember this is the mass is kg, and then this is an acceleration meters per second square. So on the other side, you should know that these things make Newton. Also from this point, we have our velocity. Remember the acceleration as change in v divided by change in time. So which is v final minus v initial divided by time final minus time initial. So you should require calculate the acceleration, the maximum acceleration, the speed, the maximum speed for the simple harmonic. So let's try to go back so that you can also start with the simple harmonic there. So I was trying to say that this okay, it's fine. So here, if you can check where the displacement of the spring. So if the displacement of the spring from, remember, this point, we call this point equilibrium. So when we extend, we apply the force downward to this part. So now another force is acting to the other side. Actually, this force want to put um, the spring to equilibrium. So which is this. So from this part, we're going to say that okay, it's fine. So from this part here, if we can check, we have the displacement of the spring, and then here we have two terms, the displacement of the spring. So from this part here, we have the force. So if the displacement of the spring doubles, so which means the force will double. So which means the displacement of the spring is directly proportional to the force, or resonating force. You should also know about it. Remember, here you might even have the time so yeah, time graph, the amplitude or the frequency with the time. So let's come to here. So here we have the vibration motion in which a system obeys the Hooke's law, oscillates with the constant amplitude. So actually, you guys, for definition, you're gonna know about it when you write your semester test. I don't know when I'm going to write the semester test. So for here we come to simple harmonic motion. So when we come here, this is called the simple harmonic motion. Is this just an acronym? So so here we have the equation. So the equation, it's x equals to a cos the angular velocity times time, because the angular velocity is directly proportional to f. This f is frequency. So it is often called angular frequency. Called angular frequency. So remember, this one is the displacement equation, and then this is the velocity equation. Also, you need to pay more attention on this part here. Remember, you have been given the velocity maximum equals to the amplitude and the angle. So you need to know that the V maximum and the V maximum is equals to the amplitude times the angular velocity. So also in this part, you also have the acceleration of simple harmonic motion. A equals to, remember, if we can, okay, so let's try to go back to unit 2. So when you were starting with unit 2, you were likely to have the velocity being v equals to 2 pi r divided by t. As you know that this t was for time, and then this r was for radius. So for you to get the acceleration, you were going to say that the velocity square divided by r. This was the formula to use. So as you know that for you to double, sorry, this is not double. For you to square the velocity, you're going to get the acceleration in which way? So remember, okay, it's fine. Velocity is meters per second. So meters per second all squared, you are going to get a meter square divided by second square. So that's why you have r down here. This is for uh remember r, it's in radius, so it's going to be m. So it's going to remove this squared on that other side so that it can be left with a meter per second square. So also here you are going to focus on something like this, where you also need to think about the SI units. So you have the maximum velocity, also the maximum acceleration. So acceleration of simple harmonic motion depends on this equation here. So this equation here assists you actually most of the time. Okay, let's focus here. So if you can check here, we have x, we have v, we have a. So we have all of the equation for the simple harmonic. Remember, this for the displacement, the velocity, and the acceleration. So this is not just an velocity. This is the maximum velocity. Also, this the maximum acceleration from that point. So before we can continue, any question? An equation? An equation? Because now we want to get on something. An equation? Okay, I'll take it as no. So, as I was saying that here we'll be also focusing on the angular frequency with which a mass on a spring will vibrate. So here, if you can remember, we also have this formula here, which has the angular velocity. So how do you get the angular velocity? So remember, lately I said that K is equals to the force divided by X. This was the displacement of the spring. This was the force, restoring force. So here you have been given the K. So this K is this K here. So remember, you should also know that K is equals to mg x. You should also know about that. This is also a force. We call it gravitational force, also a force. Doesn't matter which force is it, but as long as there is a force, it's gonna apply them. So on this part, you have K. Remember, I said K as Newton per meter. So Newton per meter there, if you can check, have Newton per meter and then divided by M. So you're going to have K divided by M. So these still are the same as, remember I said Newton per meter divided by meter. What do you think about this? Remember, this M actually it's going to cancel out this M here, and then on the other side they're going to left. Oh, sorry, I think I made a mistake there. This for a meter and this for a mass. So here I should be having the kg. So from this part, Remember, as I said, Newton is equals to kg times meter per second square. So it's going to be the square root of kg and then meters per second square divided by m divided by kg. So this and this will go away, and then also remember m and m, since it's in this way, you're going to left with the m squared divided by x s squared. So this will be the same as meters per second. That's why we have this angular there. So from that part, remember mostly here will be on angular. So from that, we're going to deal with the energy. So as you know that the energy that will be gonna be having kinetic energy, the potential energy of the string. So here, if you can check on this part, we have the elastic potential energy, which is E, okay, which is A equals to half K. Remember this K is still the same as this K here, X squared. This X squared is still there. Remember, displacement of the spring. So this depend on the position of the spring. That's why here you have the conservation of energy for a simple harmonic. So before I can go to the elastic deformation, I don't want to get confused. So I want us to go try to check whether we're going to find something. So let's try to see here. Let's hope most of you, I think you guys have started attempting these questions, because mostly of these questions that are going to come into your test on Saturday, but you'll be having some different um, values. The values might be different. They might change only the values them. They just need to know whether you're going to apply in that way, nothing else. So also there's you're going to have only one question that will never be on that learner guide of yours so far. So from this point, uh, anyone who managed to attempt these questions, anyone who managed to attempt the question on Unit 3, do we have anyone? Anyone? Okay, it's fine. I'll take it as a no. So, so far, we managed to come on this point. So, where we have our questions there. So, we have 3.1. It says a 0.5 kg mass attached to a spring with a spring constant of 8 Newton per meter vibrates in a simple harmonic motion with an amplitude of 10 centimeter. Calculate there. So remember, calculate there, and then you have letter A there. Says calculate the maximum value of its speed and acceleration. So you guys need to think about this. So before we can go through with this question, that's we can go back, harmonic motion, sorry, simple harmonic motion. So you know that the simple harmonic motion we have been dealing with this. The simple harmonic motion start from this point. As the displacement of simple harmonic motion, velocity of simple harmonic motion, acceleration of simple harmonic motion, and then from that part, they also managed to give you the mass. So remember here on this part, they say the angular frequency with which a mass m on a spring will vibrate frequency. Oh, sorry, frequency of vibration. So let's try to have a sheet. So from this part there, I'm going to take the thing that we have been given from the question. So here we have the mass, which is 0.5 kg. So we have the mass, which is 0.5 kg. So this is the only thing that you should state before proceeding with the equation. And then what do you have? Another thing. So you also have the K, which is a constant of the spring, which is 8 Newton per meter. And then go to the other side, we go to check. So they also have something, okay? They say vibrating a simple harmonic motion with an amplitude of 10 centimeter. Calculate the maximum value of its speed and acceleration. So remember, you also been given the amplitude. The amplitude is A then, which is 10 centimeter. So this is the same as 0.1 meter. Supposed to be in that way. So from here, try to get here. Okay, it's fine. So here, if we can check, we have this A here, A, and then we have A. Also on this part, we have A and then A. So this, it's our amplitude. This please. Capital letter A stand for amplitude. So remember, we've been required to calculate the maximum. So the maximum, we talk about V max and the A max. So we've been required to calculate the A max and the V max. So you check what you have. You have 0.5 kg, you have 8 Newton per meter, and then you also have A, which is amplitude, which is 10 centimeter, which is still the same as 0.1 meter. So remember, you know that on physics you deal with meters, so you need to change that centimeter into meters. So from that point, you are going to say that remember, let's try to go back and show you what you should know. From this part, remember, this is the angular frequency with which a mass m on a spring will vibrate. So if the mass m on a spring will vibrate, so now you have the equation from this point. Remember, this is an angular velocity. But you have been required to calculate the maximum speed. So as you know that you have you have 0.5 kg, which is a mass. You have the constant, you have the amplitude. So how can we get our maximum speed? How can we get our maximum speed? As you know that this acceleration is amplitude times the angular velocity squared, and then this one it's amplitude, and then angular speed. So now you need to find the angular speed. You need to find the angular speed because you don't have the angular speed. We already have the amplitude there, which is also fine. So we need to find the angular velocity. So we are going to say that the angular velocity, which is still the same as the root of k divided by m. This is the formula that you get. So you have k, you have mass, so you can even get your angular speed there. So from that point, you're going to say that k, which is 8, divided by 0.5, so over 0.5. So here you're going to get 16. So 16 is going to be 4. Going to get 4 centimeters. So remember, this is not even this, it's angular velocity, not a speed, not a maximum speed, but an angular velocity. So they need a speed, the maximum speed. So how are we going to get the maximum speed? So we're going to check the formula then. So we've been given that Vmax is equals to the amplitude times the angular velocity. So which is going to be, remember, our amplitude is 0.1. So we're going to 4, and then now we're going to get 0.4 meters per second, and that way. So another one is our maximum speed from that point. That one is our maximum speed from that point. So we have been also told that we should also get the maximum acceleration. So the maximum acceleration, we are going to say that the amplitude, which is this, and times the angular velocity, velocity squared, so which is going to be 0.1 times the 4 squared. So when you times this, so 0.4, 0.1 times 4 squared, you're going to get 1.6 meters per second squared. So as you know that this amplitude is going to be meters per second. So if this is squared, so remember it's going to be squared this point, squared that point. So yeah, so from that point you're going to have the a there, which is going to divide with the other one there, so it is going to be meters per second square in that way. This is also fine. Okay, so as I was saying that I think we're done. So this it's our maximum speed, and then this is our maximum acceleration, which was been required by the question. So as you know, 3.1 is not yet done. So if you can check down there, you've been okay so far. Any question? Any question? Any question? Any question? Do you guys have any question? Any question?
No questions.
Okay, seems like you all are fine. So from this matter here, so now we have letter B. So letter B, uh, you're going to come back from that letter B. So the letter B says calculate the speed and acceleration when the mass is 6 centimeters from the equilibrium position. So you need to understand something. Now you are calculating not the maximum speed, it's not the maximum speed and acceleration, but now it's the speed and acceleration. And then now you have been given the changing x. So this changing x, remember the displacement of a spring. So the displacement of the spring, you get it when you compress, or maybe when you pull or push the spring. So from this point, you need to, okay, sorry. Eh,